We're going to welcome Jim. Jim is a maintainer on the MicroPython project and a part-time physics student. A student of part-time physics, is that one? And then formerly SRE at Google and programmer of Grok Learning. Thanks very much, Jim.
Okay, thank you very much for the intro. Okay, so people who are in this room are going to feel a lot of deja vu from the last half an hour. We're going to go in a slightly different direction, but a lot of the topics are going to be the same. I might reinforce a couple of the same ideas. If you're new to WASM, that might be useful, but bear with us. And save some questions for the end. We'll try and together answer them. So this is a talk about distributing native code in your Python wheel. So when I install a package from pip, I install it, it downloads some untrusted piece of code from the internet that I am about to run on my computer. But sometimes I want to put native code in that. But we're Python programmers. Why do we want to do this? And the answer is that there's just some things that we cannot do in Python. Two main reasons. One is we need performance, and the second is that the code is already written in another language, be it C or Rust. And it's just not feasible for us to rewrite that in Python, and we want to distribute it as part of our Python program. And this talk is going to be built around a project that I worked on for MicroPython. This is not a talk about MicroPython, but this is a thing that we ran into while building a MicroPython tool. So we have this tool called MPyCross. It is the MicroPython cross compiler. What it does is it takes Python source code and emits MicroPython bytecode. So the output of this program is a .mpy file that you can copy onto your embedded device and then have the MicroPython interpreter on the device execute that code. It's a very useful tool, because even though the devices have a compiler on them and it's very useful to be able to put a py file straight on the device, it's bigger and takes more time and uses more memory and so forth. But this compiler is written using the same code base as MicroPython itself. It's written in C. And it's not feasible to tell people, here's our GitHub, download it and run make, install the toolchain, all that sort of thing. The second thing is people want to use this as a building block in their own Python tooling. Someone might write a MicroPython IDE and need to generate MicroPython bytecode. So we actually publish it as a library for Python users as well. And it turns out pip is just a really great way to distribute software. Everyone in the Python community, and MicroPython is part of that part of the Python community, knows how to use pip to install packages and tools. It's also an interesting case that it doesn't actually need to be really, really, really fast. Most times you compile a Python source code that might be at most a few kilobytes long. We can run quite slowly and still have an instantaneous response time. It's also interesting because it has no dependencies. It needs a C compiler to compile, and it doesn't do anything to the operating system. It doesn't use any other complicated libraries. So it's a self-contained piece of code that does a calculation. This is a bit different to Katie's talk in that we're talking about running a program that does all sorts of operating system functionality, and WASI provides an interface to do that. MicroPython, the cross compiler, you can think of much more as a thing that does a calculation and produces a result. It's just code rather than anything else. And what we currently do is we build it as an executable. You can run it at your command line. On Windows, it's a .exe. On Linux, it's an a.out. And we have a Python library that wraps that and invokes it with subprocess. So if I want to invoke, when I invoke the thing that I install by pip, it's a Python thing with a main function that just calls subprocess with its arguments straight through. We could have written this as a CPython extension, and then I would have a Python library that imports the CPython extension that is the same code as MPyCross. Instead of being packaged in a standalone executable, it's just a piece of code that I could load into Python somehow. This is almost the exact same thing that a lot of other libraries do. There's a lot of things with native code on PyPy. NumPy is probably the example that everybody's come across, or at least is most likely to come across. And NumPy is a dependency on so many things in the Python ecosystem. And NumPy has both of those requirements. One is that it's very high performance code, couldn't be written in pure Python. And the second is that it's code that was written decades ago in Fortran and has been perfected and evolved, and nobody understands it anymore, and nobody wants to modify it or change it in any way. But it works, and it's probably perfect and can be used as is. But it's really hard to distribute code. It's unbelievable to be standing here in 2023 and say, I don't know how to distribute code on the internet, or like distribute my software on the internet. Does anyone here know what a many Linux is? Does that word mean anything? Okay, so some people have built native packages. This is NumPy on PyPy. There are 24 different wheels to install PyPy. And depending on what platform, OS, architecture, phase of the moon, one of those files gets downloaded and installed on your computer. Now you can see here that I have to target different CPython versions because it's a CPython extension, so the ABI changes. I have to target different architectures. There's ARM, there's x86. Someone said to me earlier this week, it's like, you can tell you're a compiler person because when I said ARM, you said which ARM? And there are multiple versions of ARM. AR64 is different if you're on a Raspberry Pi versus if you're on an M1 Mac, for example. There's even different variations of the same platform. In the middle there is 2 versions of Linux. There's Mussared Linux and Many Linux, different glibc versions. To answer the question, Many Linux is a very carefully maintained 2014 era image of a Linux machine that if you build software on that, it will still run today, on a Linux today. But if I compiled a binary on my PC now, it would not run on other Linuxes and especially older Linuxes. Imagine you're a project like us. We write embedded code. We don't think about software distribution. We're not part of an ecosystem like this. We cannot take on board the maintenance of building a CI pipeline and a build system that can produce 24 different things. So we were talking about how to solve this and thinking about, well, how do we actually distribute code? And because we're embedded people, the conversation went something like, what if we wrote a RISC-V emulator in Python and compiled MPyCross? Because MicroPython in there is an embedded software project, and we target RISC-V and ARM and Cortex and stuff like that. And we're like, no, that's a bad idea. And then but we thought about it. Somebody else sent me this the other day, which is, if you take a Windows binary from like the early 90s, it will run on whatever the latest, Windows 11 today. They have done an incredible job of forwards compatibility. And it can use Wine on pretty much every other platform to run that 1995 era Windows binary. What if we just made a Windows compilation of MPyCross and distributed that? And then suddenly, I could even picture where we were talking about this and say, wait a minute, there's this WASM thing. I keep hearing about this WASM thing. Maybe WASM solves this problem. And it turns out WASM does solve this problem. So what is WASM? You should go back in time and watch Katie's talk and learn what WASM is, but just as a quick recap. We have a compiler, mscripton, that is a replacement for your C compiler, GCC or whatever, and built on the amazing infrastructure of LLVM and Clang, and it can produce what was originally a thing that ran in the browser, JavaScript, and now is a dedicated binary format, WebAssembly, that browsers support. And as we're going to see, things, and as Katie mentioned, things outside the browser now support. Now, this is not a talk about running code in the browser, but related to this, this is why WASM was kind of on our radar, is that we also run MicroPython in the browser as part of a thing called PyScript. It's a totally different problem and a totally different thing that we're solving, but it's really cool what you can do with WASM. At the end of the day, we just distribute code, and you have to have a way to run that code. I'm started to think of computers less as I have a computer that is like an x86 or a PC or a Mac or whatever. Rather, I just distribute code, and I happen to sometimes have hardware acceleration for it. And WASM is just one thing that can generate a thing that my computer can run. And it just so happens that we have a common way of running that on lots of different types of computers now. As I said earlier, MPyCross is just a thing that does a calculation. It takes a byte stream as an input and produces a byte stream of output. But sometimes we want to do regular C program things or regular Rust program things. And so WASI, which we're not going to talk about much, is a standard for how to replace all those things that I expect my operating system to provide. In this particular case of doing something like a computation, I don't need any of that. I just need a way to call a function and a way to get a result. So there are actually 4 different ways to run WASM in Python. So to recap, what we have is I have a Python program that I want to use a piece of native code inside. And so previously what I would have done is written a Python extension, a native extension, and linked that into my wheel. But now what we're going to do is we're going to compile our code to WASM, and we're going to try and call functions inside that WASM binary. So these 4 runtimes are PyWASM, which is a pure Python implementation of a WASM runtime. This is really cool because it has no dependencies other than things that are already on PyPy, like NumPy. But as you can imagine, writing a Python program to emulate a machine to run WebAssembly code, it's really slow. It's very easy to use and works very well, and it's a great way to learn about WASM. Although we don't need MicroPython cross-compiler to be really fast, it's too slow for MicroPython cross-compiler. The next 3 are all really, really good options. So PyWASM 3 is distributed as a source binary, so as a source wheel. So it will install everywhere. The problem is that because it's distributed as a source binary, it needs to compile. So you must have GCC and the Python dev, like the development headers installed. So as a fallback, as a way to run WASM, as a dependency to have to your program so that your program can run WASM, it's kind of a universal will run anywhere runtime. WASMA and WASM time are the sort of slightly more sophisticated ones based on projects that are built to run WASM in lots of different places. And Katie already mentioned WASM time. These use quite sophisticated things like crane lift, so they can generate native code. They'll take your WASM binary and re-emit that as native code for your machine. So you get nearly performance parity. And nowadays with things like the WASM has extensions for things like SIMD and vector instructions. It knows how to do things like set jump and all sorts of floating point features and whatever. And so you can actually run your original code as fast as it would have run if you just compiled it directly. I'm going to talk about the last 3 and highlight, like, sort of as an API sort of study of how the 3 different projects work. But all you really need to know about running WASM code is that a WASM binary is a .wasm file that imports a bunch of functions that it expects you to provide. It exports a bunch of functions that you can call. Everything is integers. It doesn't know, it's just machine code. It knows how to take an integer as an argument and return as an integer as an argument. If you want to do something more sophisticated, like deal with strings, it's an integer that points to memory that's the start of the string, and an integer that tells you how long the string is. So it's quite low level and built on these fundamentals. But as far as your Python interop goes, you only have to deal with int. And at the end of the day, memory just looks like this big list of integers that you can read and write to. So I'm going to give a quick demo. So here is a piece of native code that is doing a very, very sophisticated calculation. In this case, it's calculating the greatest common divisor of 2 numbers using Euclid's algorithm. I would write this in Python, and there would be no reason not to write this in Python, just to be really clear. But I'm giving an example of how I might be starting from some point. And what I've done is I've added this annotation to it to say inscription keep alive, and that says this function needs to be exported from my WASM binary. It's an entry point to this program. This program doesn't have a main. I can't run it directly. I'm building it as a. If you're from Windows, you'd call it a DLL. Linux would be a .so file, and it takes an int. It takes 2 integers and returns an integer. Normally, I would compile C with GCC, but in this case, I compile with EMCC. And I've got this extra flag that says no entry. It doesn't have an entry point, like a main function. And this produces this WASM file. And what's quite cool about the WASM tooling is it's quite inspectable and debuggable. There's a WASM disassembler. And this is what Katie showed in her slide, in her talk. It exports a function called GCD, which is the number 1 function. And this function is number 1 is defined, and it does some computation. I'm not going to spend time looking into this, but this is the text-based representation of my binary GCD WASM file. So if I do a hex dump, that's actually what the file is. It's encoded. Then I can use this code from Python. So what I'm doing here is I'm importing WASM 3, which is the PyWASM 3 library, and I'm creating a WASM environment. So the environment kind of represents the state of how to create a machine. I'm going to configure it with things like stack sizes and resource limits and things like that. Related to what Katie said about sandboxing, you can also do quite fine-grained control of things like how much memory the thing's allowed to allocate and how much gas it's allowed to use. It's kind of a weird concept, but you can use that as a kind of a way to limit how much work it can do. I'm loading sys.argv1, so I'm going to give the name of a .wasm file as bytes, and I'm parsing that into a module. So I now have this WASM module, which is the Python runtime's representation of my WASM file. I'm creating a runtime from it, giving it 2K of stack size, and loading my module into it. And then I'm asking, get me the GCD function. And if you've ever used any kind of like native interop or things like Swig and stuff like that, this is kind of magic. I just said, find me the function called GCD and call it. And it knew automatically what arguments it takes, what types it returns. And I can invoke that function as GCD. If I run this, I've got to give it the WASM file gcd.wasm. So GCD of 57 and 190 is 19. That's all you have to do. You can compile your C code, write literally 10 lines of Python, and execute compiled C code in your wheel. The only extra step you have to do is add that WASM file to your wheel, which is one line in your TOML file. I have a quick demo here, which is that in theory I could have written this from scratch. What I'm trying to highlight here is that it's not that I had to write it in C. Lots of languages can generate WASM, and you could even write it by hand on some sort of very optimized whatever. If I compiled this to .gcd from scratch.wasm, I could run it with the same tool. But this is not a very interesting example because I took 2 integers and returned an integer. I'm going to be working with more complicated types. Like in pycross, I have to take a Python source code file in and return compiled bytecode out. But very quickly, I'll just show you. So this is PyWasm 3. And then WASM time is a very, very similar kind of set of steps. I'm building something that's like an environment. In this case, it's an engine and a store. I'm loading a module, same concept. And then I'm asking for the things that it exports and calling the GCD function. So the next example I'm going to give is a function that does something more interesting with calling external functions and dealing with memory. So this is a function I'm going to export called calculate bytes, and I'm going to give it a number of bytes, and it's going to call a function that I'm going to provide with some chunk of data that's calculated based on those inputs. In this case, it's going to write the numbers 0 through n into my byte array and invoke a function when the data is ready. So this is sort of building up to what mpycross does. As before, this is my exported function that I can call from Python. This is saying, I expect Python to provide this function to me. I'm going to call this function when I'm ready. And I said everything works in ints. It's a uint pointer and a size t. These are both just integers, so it fits into this model of everything is just integers. Now what I have to do, though, is tell the Inscriptum compiler, and in addition, this JS library flag. And even though I'm doing nothing to do with JavaScript and nothing to do with the browser, Inscriptum is configured with a JavaScript library file that says, this is the function that I'm going to be providing from outside WASM. And then, exactly as before, I create an engine, but now I'm defining a linker. And so the linker is what lets me link my Python functions into my WASM functions. And I'm saying that there's this function called bytesReady that you expect me to provide. The function takes 2 integers and returns nothing. And I'm going to define that function on the linker, that when I instantiate my module, the .wasm file, it will now know how to call that. And so when I call calculate bytes with 20, what we're printing when the function gets called is the memory. I'll come back to what this means, but we're printing out the hex representation of my data. So just to confirm that we're getting what we want, it's the bytes 0 through 20 in a 20 byte chunk of memory. And the way it works is that my buffer was a uint pointer, but a pointer is an address in memory, and so I can index memory by doing mem.read. So mem came from my things exported from the WASM runtime. And I read from buff to buff plus bufflen, so the start pointer to the end pointer. And this gives me back a thing that looks like a bytes object in Python, and I'm printing the hex representation of it. And so finally, I'm going to run through this very quickly, which is that another quite neat thing you can do is you can use WASM as a way to run a self-contained piece of code that I can completely throw away and run again later with a brand new state. So a lot of time when you work with native code, like you're linking it into your process, and it's permanent in my process. Whereas I can use WASM as a way to temporarily run a sandbox piece of code and then run the same piece of code again. So this is a function that has some global. This is a piece of code that has some global state. But when I load it, 3 different times I'm going to instantiate this module that I've loaded and run it with a completely fresh state each time. So imagine I could write a plugin or whatever, and then the plugin can do whatever it likes with global variables and global state, and just instantiate it and run it as many times as I like. Yeah, the libraries are subtly different. So then in WASM 3, you access memory just like a memory view. The result you get back from this is in fact a memory view instance. And so, and this one uses a sort of a strange syntax where you have to tell it the signature of the function. WASMer, the other library, uses Python type annotations. So you annotate your functions with type hints, and it uses that to figure out what the interop is between the different runtimes. And then finally, as a very quick sort of explanation of how we implemented this in MPyCross. So MPyCross is a C program. It has a makefile. So we just wrote a second makefile that is identical to the first makefile, except for we say that our C compiler is EMCC instead. We had a couple more things, which is that we had to add that JS library flag to say what our imports and exports are. And there's a no entry flag as well somewhere here. Yeah, no entry as well. That's literally all I had to do. I had a C program that was written in C. I copied its makefile and I added a couple of flags and changed what the compiler is. And now when I compile it, I get mpycross.wasm instead of mpycross.exe or whatever. And then where we used to have this script, this is our Python package that we publish. It has a main that calls main. Main works like you'd expect for any other Python program and parses its inputs, and then used subprocess. Where are we? Subprocess. No, compiler native. Sorry. Subprocess.checkOutput to run a native binary. We've now implemented 3 different backends. The idea being that for any target that we support, one of those 3 WASM runtimes will be available for you. Which sounds terrible, but each one of these literally took half an hour to write. It's exactly the demo code I just showed you, with slightly more functions that it has to call and export and import. But you'll see the exact same stuff around creating a store and creating a module and so forth. And then in our TOML file, we have this one extra step, which is that we copy the .wasm file into the output directory that sits alongside the .py files. So what the code does is it looks in compiler.py. It can look in the same directory as, so you can kind of see what's going on, the absolute path of file. And so it looks adjacent to my .py files to find it. So is this a good idea? We have to take a fairly pragmatic approach on MicroPython. Like I said earlier, we're a small project, we can't spend time maintaining build systems and things for things a long way away from the type of things that we work on. The performance is excellent. You cannot, as a user, you do not notice that this is any different to the regular tool you'd use, even when you're compiling like a large number of files or big files or whatever. Performance will only get better as WASM evolves to support more instruction types and it learns more about the original code. My one little hesitation here is that by doing this ourselves the old-fashioned way, we could have supported more targets and more architectures because we could just enumerate all 24 possible abilities that we needed or whatever. We're now limited to about 7, but I think those 7 are the most common ones. And for users that have the option to install GCC and the Python dev headers, the PyWASM 3 runtime will work. There's a big to-do here, which I would have loved to have presented about, but I haven't quite figured out the details yet, is figuring out how to write a requirements.txt that figures out exactly which runtime to install. But I think this can be solved. I've had a look at a few things, and that will be an interesting coder to this. We haven't shipped this yet. We're going to find out, and I guess hit me up on Mastodon or something, or get in touch and find out how it goes for us. But the conclusion is it's so much better than what we have at the moment, which is what we're telling people is download this Git repository and run this makefile, and people look at us like, did you just tell me to write a MapReduce in Erlang? Like, what are you talking about? And it's very, very simple. It's one Python dependency, and it's quite easy to introspect. The tooling is good. Yeah. So that's it. I'd love to answer questions. Katie will come up and help join.
Thanks very much, Jim. I'll invite Katie up and we'll share the mic, or she can have the mic in back. Do we have questions? Hands up. Yep, just at the back.
You actually missed some methods that you are not providing, and where are they coming from? Where's malloc and free coming from?
So malloc and free are provided because the runtime provides malloc. The runtime provides a way to get memory, and malloc is available to you in your WASM binary. That's actually a very good observation. In my bytes example, what happened was I wanted to return a byte array, so I allocated it. The WASM runtime is just this giant array of bytes that it can allocate and grow as it needs to, and it provides the alloc implementation for you. What's quite useful, and what we do in pycross, is that we actually just export malloc directly to the Python level, and so when Python wants to get some memory to read and write into, it calls malloc directly.
I was wondering what the debugging story is like and how you go about getting errors back from your library to users.
So when you make an error, for example, in a function that the WASM module imports, if you have an exception, it gets very, very confused because you've now got a stack trace that involves Python back through the WASM runtime, through C, then back into your Python code that initiated it. It's quite challenging. And the other thing is when you disassemble the WASM code, you can't see it. What I've been doing is debugging the C code using our normal build. But I'm not aware of, for example, a WASM debugger. One thing you can do is you can take your .wasm file and you can load it directly in the browser. At the end of the day, it is just WASM. You have to, and if you provide the same imports and exports, and I think there are better tools in the browser. But yes, debugging is not a well-answered story at this point. Yeah.
Yep. I haven't had much experience debugging WASM directly because I've mostly just been running CPython. But yes, the browser tools are there. You have the same kind of interaction between if you're running JavaScript and you're calling a WASM function, you also need to sort of allocate the memory and copy the strings across and then send pointers into WebAssembly. It's just for when you're building for the browser, those functions in JavaScript are kind of created for you a lot of the time. So if you build Rust and you compile it to WebAssembly, it has convenient functions for those. But yes, I think there is some kind of debugging tool for WebAssembly directly, but I've not used it, so I don't know. Yeah. I
have an anecdotal story of one of the runtimes, the very first one that's written in pure Python. It didn't implement some part of the WASM spec. I didn't know that. And I ran it worked for my test programs, and I ran pycross, and it crashed with a legal instruction. So the answer to that is I had to debug the way you would debug Python code. So, yeah.
We're out of time, I'm afraid.
Oh, okay.
But thank you so much for the questions. Thanks, Katie. Thanks, Jim.
Thank you.
Once again. And we're going to reconvene again. Oh, I need to give you the
cool. Thank you so much.
The ceremonial mug and thank you cards.
Thank you.
Great job.